In game theory, Battle of the Sexes is a two-player coordination game. Imagine a couple that agreed to meet this evening, but cannot recall if they will be attending the opera or a football match. The husband would most of all like to go to the football game. The wife would like to go to the opera. Both would prefer to go to the same place rather than different ones. If they cannot communicate, where should they go? In each cell, the first number represents the payoff to the wife and the second number represents the payoff to the husband. This representation does not account for the additional harm that might come from not only going to different locations, but going to the wrong one as well. To account for this, the game is sometimes represented as in Battle of the Sexes. Some authors refer to the game as Bach or Stravinsky and designate the players simply as Player 1 and Player 2, rather than assigning gender. Equilibrium analysis. This game has two pure strategy Nash equilibria, one where both go to the opera and another where both go to the football game. There is also a mixed strategies Nash equilibrium in both games, where the players go to their preferred event more often than the other. For the payoffs listed in the first game, each player attends their preferred event with probability 3/5. This presents an interesting case for game theory since each of the Nash equilibria is deficient in some way. The two pure strategy Nash equilibria are unfair. One player consistently does better than the other. The mixed strategy Nash equilibrium is inefficient. The players will must coordinate with probability 13/25, leaving each player with an expected return of 6/5. One possible resolution of the difficulty involves the use of a correlated equilibrium. In its simplest form, if the players of the game have access to a commonly observed randomizing device, then they might decide to correlate their strategies in the game based on the outcome of the device. For example, if the couple could flip a coin before choosing their strategies, they might agree to correlate their strategies based on the coin flip by, say, choosing football in the event of heads and opera in the event of tails. Notice that once the results of the coin flip are revealed, neither the husband nor wife have any incentives to alter their proposed actions. That would result in miscoordination and a lower payoff than simply adhering to the agreed-upon strategies. The result is that perfect coordination is always achieved and, prior to the coin flip, the expected payoffs for the players are exactly equal. Working out the above, let us calculate the four probabilities for the actions of the individuals, which depend on their expectations of the behavior of the other, and the relative payoff from each action. These four probabilities are: the man goes to the football, denoted by MF. The woman goes to the football, denoted by WF. The probability that the man goes to the football game, MF, equals the payoff if he does, divided by the same payoff plus the payoff if he goes to the opera instead. We know that she either goes to one or the other, so. Similarly, this forms a set of simultaneous equations. We can solve these, starting with, for example, by substituting in the equations above, solving the last equation for yields. Knowing that, we deduce. Then we can calculate the probability of coordination as, and the probability of miscoordination. And just to check our probability working, so the probability of miscoordination is as stated above. The expected payoff E for each individual is the probability of each event multiplied by the payoff if it happens. For example, the probability that the man goes to football and the woman goes to football multiplied by the expected payoff to the man if that happens. The payoff is just one for both, from the table above. Burning money. Interesting strategic changes can take place in this game if one allows one player the option of burning money, that is, allowing that player to destroy some of her utility. Consider the version of Battle of the Sexes pictured here. Before making the decision, the row player can, in view of the column player, choose to set fire to 2 points, making the game burned pictured to the right. This results in a game with 4 strategies for each player. The row player can choose to burn or not burn the money and also choose to play opera or football. The column player observes whether or not the row player burns and then chooses either to play opera or football. If one iteratively deletes weakly dominated strategies, then one arrives at a unique solution where the row player does not burn the money and plays opera, and where the column player plays opera. The odd thing about this result is that by simply having the opportunity to burn money, the row player is able to secure her favored equilibrium. The reasoning that results in this conclusion is known as forward induction and is somewhat controversial. For a detailed explanation, see P8 section 4.5. In brief, by choosing not to burn money, the player is indicating she expects an outcome that is better than any of the outcomes available in their burned version, and this conveys information to the other party about which branch she will take. Battle of the Sexes game with ambiguity. Decisions are said to be ambiguous if there are no objective probabilities given and it is difficult or impossible to assign subjective probabilities to events. Kelsey and LaRue report an experimental test of the influence of ambiguity on behavior in a Battle of Sexes game which has an added safe strategy R available for player 2. The paper studies the behavior of subjects in the presence of ambiguity and attempts to determine whether subjects playing the Battle of Sexes game prefer to choose an ambiguity-safe option. The value of X, which is the safe option available to player 2, varies in the range 60 to 260. For some values of X, the safe strategy is dominated by a mixed strategy of L and M, and thus would not be played in a Nash equilibrium. For some higher values of X, the game is dominance solvable. The effect of ambiguity aversion is to make R attractive for player 2. R is never chosen in Nash equilibrium for the parameter values considered. However, it may be chosen when there is ambiguity. Moreover, for some values of X, the games are dominance solvable and R is not part of the equilibrium strategy. For a detailed explanation, see. It was found that R is chosen quite frequently by subjects. While the row player randomizes 50-50 between her strategies, the column player shows a marked preference for avoiding ambiguity and choosing his ambiguity-safe strategy. Thus, the results provide evidence that ambiguity influences behavior in the games.